Today we are going to learn about a very interesting problem, and that is of string matching. Okay, so string matching is used quite a lot and in lot of different fields. So one very basic method that we all know is by brute force. Okay, but here we will look at one of very interesting algorithm which is known as Horspool algorithm, and it is very much similar to Boys-Moore algorithm also. Okay, so you will understand from this the table construction for both the Horspool's algorithm and Boys-Moore algorithm, that is very famous string matching algorithm. In fact, it is used in a lot of virus detection using pattern matching. So this is the algorithm that is used. So let's see what is string matching. So you will be given a text. Okay, so like the text A B A C A B D A C C, something like this, a big string. You will also be given a pattern. So with this pattern, you have to now find, is this pattern present in this string or not? Okay, so this is the idea. So let's see. So text is S0, S1, S2, S3 till Sn minus 1. Okay, and how we try with brute force? So this is the text. What we do, this is A B C A B C A B B A. So we have this as the text, and then we have a pattern BCA. Okay, so you have to find, is there a pattern BCA of 3 letters? Does it exist? The simplest algorithm. This is the text. If we use a sliding window, it starts with the first character of T. We have this window. Now what you need to do, just see if from right to left we do. So is C is equal to A? So no. So this means this pattern doesn't match, because for pattern to match, all of them should be equal. So we can match each letter from left to right or right to left. Both are fine. So from left to right, is A is equal to B? No. Okay. So if any one of them doesn't match, it's not a pattern. So here for Boys-Moore algorithm or for Horspool algorithm, we will use this, from right to left we will match the pattern. So C is not equal to A in the first letter itself. It doesn't match. So we slide the window by 1 to the right. BCA, now we see A is equal to A corresponding, C is equal to C, and B is equal to B. So BCA matches the pattern, and hence we say now that we have got one pattern. But still we can move further. We can slide the window once again to the right. So it will come here BCA. B is not equal to A, so this will not match. Again, let's see if we move further 2 shifts. So BCA is matching. In the last final shift, BCA is not matching. So we got 2 shifts which are matching. So this is the method. And now if the length of this is N, this is M, so you can understand that for one matching with shift, if this window is somewhere, so to match, if it is the same, this pattern is there in the text, so you have to compare M text, isn't it? And this sliding window can, how many shifts can it make? So 1, 2, 3, 4, 5, 6, 7, 8 shifts. Okay, so it can make maximum of, so this N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So around M minus, so N minus M plus 1, something like this, it can make the number of shifts. Okay, so you have the algorithm which will be O of M into N minus M plus 1. So mostly it will be O of M into N. Okay, so this will be the time complexity if we use the brute force method. Okay, so if N is very large and M is large, so this will be a complicated algorithm. Big, basically you have to try out lot of shifts But what is done in now the Horspool's algorithm? So if we can find that in the text pattern, if we can see that in the pattern, if we can pre-process it and find some useful information, we can make shifts larger than 1 without missing any of the patterns. So that is the beauty and the key idea. The key is shift of length greater than 1. Okay, and of course maximum it will be m. So what happens? Let's see. So if we have a pattern which is barber, okay, which will cut your hair. So barber, if it is there, and let's say we have some string which goes on like this till Sn minus 1. So this is the text string, and in that, let's say that our window was somewhere in which the last string, the last character of the text is S and we have R there. So these two doesn't match, isn't it? S is not equal to R. So we take the from the pattern window whatever is matching there, the last character C. So here C is equal to S. So we compare these and we start from right to left. So S is not equal to R. So what happens now? So let's see how much shift can we make. So we see that S is not at all present in the barber pattern. So what happens if we make a shift by 1? So now E will be now coming to face S. E is not equal to S because S is in fact not there in any of the, it is not present in the pattern. So now with 2 shift B will come to S, still it will be not matching, it will be rejected. With 3 shift R will match S again. So what will happen with shift of 3 also, it will not work because R is not equal to S. Then with shift of 4 we will have A aligned to S, again S is not equal to A. If we shift by 5, so B is aligned with S, it will also not match. Okay, so that's the thing. So it means that if the character C is not present at all in the pattern, then you can directly make a shift of how much? Of M. Okay, so here it is M is equal to 6 and we can make a shift because 1, 2, 3, 4, 5, 6, its length is 6. So we can make a shift of 6 directly because this S, it is not found in this whole pattern, so it will never match, and we have to just shift so that S doesn't come in the alignment anymore. So we can make a shift of 6. Bingo. So it's something great. You're not now moving very slowly. Your window can move fast. When one step, just go directly M steps further, M shifts. Now let's see. We have some text pattern in which the window is now aligned here and the last character C is equal to B. Now we see that B is present in our pattern because B is occurring twice. So B is present, and what happens? Now if we slide, how much shift can I make still so that I don't miss any pattern if it was found? If I make a shift by 1, again E is not equal to B, that will not work. But if I make a shift of 2, so this B will now get aligned to this B. So again the pattern can match. Okay, so shift of 2 will be fine here. So we have to, this B, we will try to match if this B is present in this barber or the pattern. So we will try to align the rightmost B here to this B. Okay, so we will have a shift of 2 so that this B now comes under this B. So this makes a shift of 2. Again, it is good enough, so better than one shift. Case 3, that character C, which is the last aligned character with the pattern, if this C is the last character in pattern but no C is present in the first M-1 characters. So this is another case, case 3. So let's say we have R is present and they both are aligning. Good. We move further. So what happens, this R is not there in the first m minus 1 characters. So how much shift can I make now? Again, if we make a shift of this, E will come here, then D will come here, A. So because there is nothing in the first m minus 1 characters, there is no R. So again you can make a shift of m. Bingo. So that's very good news. You can make a shift of m itself, and it's much better than 1. The case fourth, the last case, is that if C, the last aligned letter, is also present in the first m minus 1 characters, then what we should do? Again, try to align the rightmost letter that is present in the pattern to that C. Okay, so for example, again R is here, it is matching, but R is also here and here. Okay, so it's occurring more than once in the, not just the last but other places also. So again we want to align this R to now this R. So we have to make a shift of how much? This R, if I want to make it here, so 1, 2, 3. So make a shift of 3. So well, here is this algorithm now. Okay, so this is the basic idea of both the Horspool algorithm and Boyle-Moore algorithm. Okay, so this is the idea. So make a table. Okay, so where we know that, okay, if it is the last C that we are matching, if it is not there, how much shift we have to do. And because this will be occurring for lot of times, so we pre-compute a table and use that table directly to find how much shift will be there. Okay, so this is the pre-processing. So we have this C now, the last letter can be anything from the alphabet of A, B, C, D, E, whatever you can write. Okay, so that is the alphabet. In that you have to write the table for all. So this input pre-processing is done. So we have a string P. P is the pattern and size is the size of the alphabet. So for example, just for simple A, B, C till Z, you have 26 letters, the uppercase and smaller case. So if we are just writing in, let's say, smaller case, so your alphabet size is 26. If you take a space there, it will become 27. So table will be of the size of your alphabet. So now we will compute shift size for all letters. So what we do in the first for loop, for all the letters in the alphabet, we make table for that letter is equal to m. Because if it is not present, if that letter is not present in the pattern, you can directly shift by m, that the pattern length. But for letters which are present, so what we will do? So for example, barber. So this is 0, 1, 2, 3, 4, 5 and m is equal to 6. So we shift for all this. For R, for example, we make a shift of how much? So it will be 6 minus 1 and minus J. So J here is the position of R, the rightmost position of R. Okay, so it will be here. So R is the 2. So it will be 4. Okay, so let's try to see this thing. So here is the table. So barber is our pattern. So we have table all the alphabets A, B, C, D, E, F, G till Z and a space. Now, so A. So A occurs where? Here. So its position is J is equal to 1. M is 6. So 6 minus 1 minus J, which is equal to 4. So you will shift for A, you make a shift of 4. For B, so B is present, the rightmost B, so it is here. So we make, so B is now at 0, 1, 2, 3. So B is at 3. So 6 minus 1 minus 3. So 2. So we have a 2 shift. C is not present in barber. So make a shift of 6. E is present. So its value is for J is 5. In fact 0, 1, 2, 3, 4. So 6 minus 1 minus 4. So it is 1. So E is 1 here. For R, it is this one. So except the last character, where is it found rightmost? So R, here it is. So 0, 1, 2. So 6 minus 1 minus 2 it is becoming 3. So R is 3, and for all other it is 6. So now let's get started with the example which will help you understand everything in a nutshell. Jim saw me in a barber parlor. Okay, so this is the sentence, the text. Jim saw me in a barber parlor. Okay, so he found me. But now you have to find, is barber the pattern present? Okay, Jim found me, but you have to find barber in this string. So barber, now again we start alignment. So B is now the first letter, A, R, B, R. Okay, so we will now start comparing from the last letter. A and R are aligned, they are not equal. So A is the last letter. Just see from the table the shift by 4. So 1, 2, 3, 4. B comes here by shift of 4. Barber, now E is aligned to R, the last letter. E and R are not equal. See the shift of E, 1. So we make a shift of 1. E comes here, so that E and E are now aligned. So we will try to now see, is it happening? So underscore and R are missing, but we try to align E with E, so that at least it's possible that okay, we are aligning something, so there might be a match, but it's not happening. R and space are not matching. So underscore, there is no underscore in the pattern. Shift by 6 directly. Barber now comes to this place, barber. Again R and B are not matching, but B, if it is there, shift by 2. So barber comes here. R and R are matching, good. A and E are not matching. So last letter was R. If you have an R, shift by 3. Okay, so that this R is now aligned to. So you have to make a shift such that, so this B gets aligned to. So now let's see what is happening. B, so we have a B, so with B you have to make a shift of 2. I made a shift of 2. Barber, R and R are matching, A and this are not matching, so R again. So for R you have to make a shift of 3. So I come here, 1, 2, 3. So barber, now R is matching, E is matching with this E, B is matching here, R and R matching, A and A matching, B and B matching. Bingo! So it is matched now, and you have found me also, and Jim has found me, and you have found barber here. Okay, so now for any random text, so this requires now theta of n time for finding the match. Okay, so this is the average running time, okay, for this, for finding the pattern. And if you see, for this table creation, it is just done once, and that's called the pre-processing, and it will be taking time of what this size is. So theta of size, so this is the size of the alphabet it will take. Okay, so this is running just once, then after that you can match the pattern in theta n time. Okay, so that is a great news. So now you know how to do pattern matching, at least much faster than the brute force method, and this runs in theta n times on average, whereas that was theta n into m. So you are getting such a great benefit. So theta n into m, so this will be, if m is large, 10, so it will be coming 10 times of this. Okay, so this is great. Pattern, the pattern length increases, this will be much more. Okay, so I hope you like this video. It is very interesting, pattern matching. So if you like this video, please subscribe to my YouTube channel. Tell it to your friends also to watch my YouTube videos. Thanks a lot.